Hello, my name is Lucas Borini, and with my partners Connor Danelson and Preston Edwards, we are presenting on Prompt B, involving the punishing of infants, and more specifically, how interactions between a population that punishes aggressors who victimize others, how interactions between those populations affect their population numbers and then cultural dynamics. We had the privilege of being coached by our instructor, Major Brittany Oletti, and we're representing the United States Military Academy at West Point, New York. So some background on the problem. This is based on a publication in Nature Human Behavior, which is a scientific journal. It concluded that humans as young as 8 months old already have an inherent desire to punish those who hurt others. And so this begs the question, if we have a population made up of punishers and aggressors, how do they change, and how does their population sizes change based on the interactions between them? And then that leads to another question, how does the severity of the punishment affect population sizes, growth of the population, and general dynamics between the two populations?
Hello, my name is Connor Danelson, and I will be going over the transform part of our project. First, we had to make our assumptions. Our first assumption was that there are no outside groups present unless specified, so this shows that the aggressor and punisher populations were not influenced by outside groups. Another assumption that we had is that punishers only punish aggressors, so this creates a one-on-one interaction between the punishers and aggressors for the model to work. We also assume that the punishers decrease as a result of decreasing aggressors. So in the absence of aggressors, the population of punishers will naturally decrease over time. And we also assume that the number of aggressors increases unless punished by punishers. So aggressors will increase if there is no looming threat of punishers. For our variables, first we established that x of t is the population of punishers over time, and the x prime of t is the change in the punisher population. Y of t is the population of aggressors over time t, and y prime of t is the change in aggressor population, and t is time since the start of interactions within the population in months. For our first model, we had the logical Volterra predator-prey model, which is represented by x prime of t is equal to negative ax of t. This term represents how, in the absence of aggressors, the punishers, x of t, will naturally decrease. And then when the two populations of punishers and aggressors interact, this will result in a positive change for the punisher population as represented by p times x of t times y of t. And then for the punishers in this basic model, or the prey, which is the aggressors, will be y of t. And this is shown by c times y of t, which shows that naturally in the absence of punishers, the population of aggressors will increase. And then for every interaction between the aggressors and the punishers, the population of aggressors will decrease. And then for our second model, which was altered to show the cultural shift in attitudes over time, we showed that over time, the number, if a cultural attitude shifted towards a more propensity for punishing, or people are more likely to punish in the society over time, we showed that over time, the decrease of punishers over time t will naturally increase, and then the number of aggressors, the change in the number of aggressors will also decrease. So over time, this would result in more punishers and less aggressors. For our parameters for these, we had A, which we showed was the rate of decline, B, which was the rate of punishers per interaction, C was the rate of aggressors, and D was the rate of decline for aggressors per interaction with punishers. We also had in our model M and N, which were initial number of punishers and aggressors at time 0 respectively. And for our the competition model, we had to create new parameters. We had R1 and R2, which is the growth rate of punisher groups A and B respectively, K1 and K2, which is the carrying capacity of punisher groups A and B respectively, and A1, which represented the influence each punisher group had on each other. For this model, we used XSOL and ZSOL to show the two groups of punishers, with one having a higher propensity of punishment than the other, and then we plugged these into the modified predator-prey, with Z of t now representing the population of aggressors, and X of T and Y of T being the population of the two competing Punisher groups.
I'm Cadet Preston Edwards, and I'll be going over the solve portion of our model today. So for our initial model, we see there's not really a whole lot of complexity going on here. It's it's the same kind of vertexes and troughs as you see before. There's no real exhibition of any like cultural shifts or anything. But we do see, as the peaks in Punishers means the aggressive populations immediately begins lowering down. But at the same time, we're not seeing, there's no complexity going on. Nothing real. It's the same kind of cyclic graph over and over again. For our improved model, we're seeing differences in populations over time. The aggressor population is decreasing greatly throughout over time, but it's still going down to zero and showing that cyclic motion. But with the Punisher population, it's kind of steadily moving up over time. So we're adding a little bit of complexity. But for our most complex kind of model, we have the additional Punisher group. So our first Punisher group, Group A, is not as severe. It will not punish severely as the other groups, and as a result, it isn't able to kind of use the resources of aggressors as much. So therefore, it kind of levels out to its initial population, as seen by the blue line. But for the green line, with the more severe punishment, Group B, it's able to steadily increase and increase its population. And the aggressor population, as seen by the red line, is steadily moving downward, again showing the kind of that cyclic motion. All right, and that concludes our solving portion of our model.
Okay, and to finish it, I'm just going to be interpreting our models, kind of talking about what they mean in a real-world context. So as all the models kind of showed, both the severity of punishment and the ratios in population between punishers and aggressors impact the behavior of the aggressor population. And so in our initial model, where we have the number of punishers in blue and aggressors in orange, we can see an inverse correlational relationship, which basically means if we increase the number of punishers, we decrease the number of aggressors. And it's slightly offset because if you think about this in the real world, the trends of the aggressor population are due to reactions to actions by the punishing population. And so that takes time to take effect on the actual population size, which is why it's slightly offset. But as Preston said, that's not really accurate in the real world. We just have sort of the population levels dropping and rising to the same level every time, which wouldn't really make sense over time. And so our improved model accounts for that. We start to see in the punishing population, if we look at the peaks of their population at different intervals, then you see like a linear increase, and then conversely you see a linear decrease at the peak populations at intervals for the aggressing population. And so that kind of shows how within a society over time, a population with a higher punishing to aggressor ratio, we'll see an increase in punishing population and a decrease in aggressing population. And then finally, the competition model is comparing different trends in the population with respect to different severities of punishment. So the blue graph represents the least severe of punishment, which is why we kind of see the population of punishers taper off. It's being overpowered by the aggressor population. Similarly, the green graph, while it does have higher population levels and more variability, is still slightly being overpowered by the aggressing population, and you can see like a bit of a decrease in their like maximum populations over time. And then finally, the orange represents the most severe punishment, which is where we actually see increased variability and increased maximum populations over time. So these are our works cited. Thank you very much, and thank you very much to our instructor, Major Oletti.